Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In the previous module we derived equation for voltage as well as an equation for current, which I gave you as an exercise on the transmission line. If you recall what those equations are, that equation tells you on the left hand side how the voltage would be changing, voltage being a function of both Z and T on the transmission line. So, on the left hand side of the equation you have the voltage changing as a function of Z. Remember, Z is the axis along which the voltage or the axis of the transmission line that we have considered. The right hand side of this equation will have LC into del square V by del T square. Again, V is a function of both Z and T, right. The left hand side is telling you how the voltage is changing along Z, and the right hand side is telling you how the voltage is changing along time. The voltage is actually a function of both Z and time. Now, how do we solve this equation? Now, mathematically these equations are called as partial differential equations of the second order, and mathematicians have come up with various ways to solve this equation. We will not go through the solution of this equation at this point, but instead I will tell you the solution, and later in an exercise you can demonstrate that the form of the solution that I give you is actually satisfying this particular equation. Incidentally, this equation is called as a wave equation for the voltage V. A similar equation will be there for current I. Now, this particular wave equation will admit solutions of the form f of t minus square root LC into Z, or f of t plus square root LC into Z. It will also admit solutions of the form Z minus t by square root LC, and you can very clearly see that I have just interchanged the positions of Z and t from the function f in this function g. It will also satisfy, or it will also admit the solution of the form g Z plus t by square root LC. You can actually substitute these functions into them. We only demand that these functions f and g be reasonably, mathematically reasonable, physically reasonable, that they do not have infinities anywhere or they are not physically unrealizable. These functions are assumed to be physically well behaved, mathematically well behaved. Okay. Let us consider what is the implication or what is the meaning of this type of solution. So, let us consider, for example, that the voltage V at any point on Z and T of the transmission line will be of the form G of Z minus T by square root LC. Okay. We do not really care about what is the shape of the waveform here or shape of the function g here. We are only interested in looking at what would happen if this is the kind of solution that will be satisfied by the voltage, and what is the implication of this one. Let us say I somehow freeze time, right. By freezing time I mean I take a particular value of time. I can take any value of time for this function. So, but let me assume that I am taking t equal to 0, and then I look at the entire transmission line. So, I have a transmission line here and I have frozen time at t equal to 0, right. Now, what will happen to the function then? Then V at Z at time t equal to 0 will be some function g of Z. So, if you actually have a transmission line in this way and Z axis is one that is travelling in the direction that I have shown, then you can see that this function g of z would be present along the transmission line. Let us say that the function g of z is peaking at some arbitrary position z0. So, at some arbitrary position z0 the function g of z is peaking. Now, I will increase time from 0 to some additional time delta t such that delta t is greater than 0. Then what will be the shape of this one? Now, you look at what will happen to the function g then. G Z minus delta t by square root LC will be the new function, correct. And from your earlier signals and systems you would know that if g of z would represent a function of z in this particular manner which is peaking at z0, g of z minus delta t by square root LC will be the same function g of z, except that it has got delayed or shifted. So, now earlier this was peaking at z0, now this function would peak at z0 plus delta t by square root LC, right. So, it would actually be peaking at this point and the shape of the function would remain the same. The essential point is that if earlier the peak was situated at z0, now the peak is situated at z0 plus delta t by square root LC. So this is the shift with respect to delta z, or with respect to z axis, the amount of shift is delta z, that needs to happen such that the peak gets shifted by a certain amount, which is given by delta t by square root LC, right. And to which side is this shift happening? Now suppose I go from t equal to delta t to t equal to 2 delta t, right. So I increase the time from delta t to 2 delta t, and what will happen to the position where the peak would be present? It would further shift towards the z axis. So as delta t increases, the shift of the waveform also happens in the positive z direction. Therefore this kind of a thing would represent a wave behavior with a wave moving along the positive z axis. Okay. So the shift is happening along the positive z axis, and the voltage is actually a wave, right, with a particular wave shape. That wave shape is not important for us, but it is a wave which is moving along positive z axis. Okay. So this is a wave that is moving along positive z axis. Now instead, if you had started off with the function, let us say g of z plus t by square root LC, at t equal to 0 you would still have the original function g of z, but if I now increase my time, the peak should now occur earlier in z, correct. So the peak would now occur at minus z0 plus delta t by square root LC, right. So this is a wave which is actually moving in the negative z axis, and therefore this particular voltage would correspond to a wave which is moving along minus z axis. So to summarize, transmission line equations for the voltage admit a class of solutions which are given by g z plus or minus t by square root of LC, or equivalently f t plus or minus square root LC into z, okay, with the plus sign standing for waves moving in the minus z axis, minus sign standing for waves moving in the positive z axis. By the way, what would be the velocity of this wave? It is kind of very easy to understand that velocity, right, or derive that velocity. We, for concreteness, we will assume that z0 equal to 0 is the position at which the original function g of z would be peaking, right. So originally g of z would peak at z equal to 0 along the transmission line. Okay. Now at t equal to delta t, so this was the situation at t equal to 0, and the function g of z was peaking at z equal to 0 or z naught equal to 0. Now as I increase t from 0 to delta t, my function has shifted to delta t by square root LC. This is the change that has happened in delta z. The location of the peak has changed by a distance delta z, which is given by delta t divided by square root of LC, and if you take the ratio of delta z by delta t, which will give you the velocity at which this peak is moving, this particular point is moving towards or along the positive z axis, will be the velocity of the wave, and that velocity is given by 1 by square root LC. It is kind of quite surprising that the two parameters L and C of the transmission line, L and C of the transmission line, determining the velocity of the voltage. And you can also show that because the current satisfies the same set of equations, right, instead of V of zt you replace V of zt by I of zt, the equation would be the same, therefore the velocity of the current would also be the same. So whatever the voltage that is moving as a function of z and t, a similar waveform would be available for the current as well. So current would also be moving along either plus z axis or along minus z axis at the same velocity of 1 by square root LC. So we have seen that voltages and currents on the transmission line are no longer just a z independent quantities, they are actually waves which are moving either along positive axis or along negative axis. Okay. So that is the idea of a voltage or a current wave on the transmission line. Okay. Now let us actually specialize these functions g or f into a very specific type of functions. These functions that we would want to specialize are the trigonometric functions cos or sine, or equivalently the complex exponentials. So I would like us to consider functions which are of the form cos omega t plus or minus beta z. Your cos can also be sine with the argument of omega t plus or minus beta z, or we will consider the corresponding exponential, complex exponentials of e power j omega t plus or minus beta z. This class of solutions in which the function g or f has a particular form of a trigonometric cosine, sine or a complex exponentials are called as sinusoidal waves. Okay. No doubt something that would be very familiar to you from your earlier wave theory classes. So, sinusoidal wave is the one that would be varying as a function of cosine or a sine or equivalently as a complex exponential. Again, you can see that the plus sign would represent a wave that is propagating along the minus z axis, and a minus sign would correspond to a wave that is moving along the plus z axis. Okay. There are couple of additional constants that we have seemed to be introducing in an arbitrary manner. Okay. It is not very arbitrarily. I will tell you what these omega and beta are. This omega is what is called as the angular velocity, and this is called as the angular frequency, and this angular frequency is given by 2 pi into f, where f is the frequency measured in hertz. Angular frequency is one that is actually measured in radians per second. Okay. Beta is called as the propagation constant of the wave. In this particular case, propagation constant beta happens to be a constant itself. In general, beta need not be a constant, it can be a function of frequency. When beta is a function of frequency, then in a non-trivial way, if it is a function of frequency, then it gives rise to a phenomenon called as dispersion, as we will see later on. This propagation constant and the angular velocity are angular frequency are related to the constants of the transmission line L and C in the fashion that omega by beta is given by 1 by square root LC, okay, where 1 by square root LC is also called as the phase velocity. Why would it be called as the phase velocity? Go back to this one. As delta t changes, delta z also changes in a proportionate manner, so as to keep the peak of this function moving along. So, if you actually imagine that you are a little person who is able to sit on this particular peak and travel along the wave, you would see that the velocity with which this particular point or velocity with which you will be moving along the wave peak, right, along the wave peak will be given by 1 by square root LC, and that is the phase velocity. If you have ever surfed in an ocean, then this phenomenon could be quite familiar to you. You know, you are moving along the wave and you position yourself at the top of the of the wave, and the wave is actually carrying you. While the wave is carrying you towards the shore or towards the sea, does not matter, but if you are on the peak, the velocity with which you move along that particular peak will be given by this 1 by square root LC. Okay. I mean, in a transmission line, if you imagine yourself on that one, on a seashore that velocity will be quite different. So, this is the meaning of what we call as a phase velocity, and it is the ratio of omega to beta that determines what is the phase velocity, and in this particular case it so happens that this ratio omega by beta is given by 1 by square root LC. Okay. So, this is something that you should remember. We will later on see that the ratio d omega by d beta, which tells you how the velocity itself is changing, will be the one that will decide what is called as the group velocity, and it is this group velocity that will tell you how a particular packet or when you have a modulated wave, the peak of the modulated wave, how quickly or how fast it is moving is determined by this group velocity. It also turns out that group velocity itself might be a function of frequency, in which case this change of group velocity with respect to the frequency omega angular frequency or the regular frequency f, when the group velocity itself depends on this frequency omega, this gives rise to what is called as dispersion. We will see all these things later on. Okay. Now, coming back, our voltage V as a function of z and t is now given by some constant V0 cos omega t minus beta z if the wave is propagating along plus z axis. It will be given by cos of omega t plus beta z if the wave is propagating along minus z axis. To denote a wave which is propagating along plus z axis, let me introduce a superscript to the amplitude V0, call this as V0 plus, and to denote a wave amplitude which is propagating along minus z direction, let me denote it by V0 minus. Okay. Since the wave equation happens to be linear, our mathematician friends will tell us the total solution will actually be a linear combination of these two. That is, a wave equation can support both positive z axis wave as well as a wave which is propagating along minus z axis. So, this wave we can call this as V plus zt, indicating that this is a positive z travelling wave, and this would be a V minus zt that would be propagating in the minus z axis or in the minus z direction. There is one additional thing which I want to introduce at this point. We will now consider, from now onwards, we will consider all waves to be at the same frequency omega. Okay. Everything in the transmission line problem that we will consider from now on, at least until the point where we stop considering this one, the frequency domain behavior will have the same frequency omega. Okay. And it is kind of painful for us to carry out this or carry along this omega t factor. Okay. And moreover, the notation of complex exponential is much better suited, or it is much suited for discussing the problems mathematically. So, it kind of simplifies our mathematical expressions. Therefore, instead of considering cos and sine, I would like to move on to consider the complex exponentials. Okay. In terms of a complex exponential, I can write my voltage V of zt as real part of V0 plus e to the power j omega t minus beta z, assuming that I consider only wave propagating along plus z axis. Correct? This is true because if you go back to this expression V of zt here, you see that this expression would be the same because e to the power jx, the real part of that, is given by cos x. Here x is equal to omega t minus beta z being the argument of the complex exponential. If I want to represent in the complex exponential form for a wave which is propagating along minus z axis, simply replace omega t minus beta z by omega t plus beta z. Okay. E power j omega t will be a constant for us, I mean it will be a constant factor for us to include everywhere. What people do in order to simplify the notation further is that they drop this real denotion, that is they will not denote it by real. Okay. They also drop this factor e power j omega t. Okay. When I drop real as well as I drop this factor e power j omega t, what I get is simply this V0 plus e power minus j beta z, which would be a complex number for every value of z. If I say z is a constant at some particular point on the transmission line, then this V0 plus e power minus j beta z will be a complex number, and this complex number is called as a phasor. Okay. What is the advantage of using a phasor? Consider what happens to the situation where I am trying to find out what is the partial derivative of the voltage with respect to time. Okay. So, my voltage was of the form V0 plus cos omega t minus beta z, but when I differentiate this one with respect to time, what I get will be minus omega V0 plus sin omega t minus beta into z. I hope we know that we agree to this one, right? Now, this right hand side can be written in a complex notation by calling this as real part of j omega V0 plus e to the power minus j beta z e power j omega t. I just removed e power j omega t minus beta z into two factors, right? E to the power a b, so e to the power a into e to the power b is e to the power a plus b. Correct? To obtain the phasor form of this, I will drop real and I will drop this e power j omega t factors from this expression. When I drop these factors, the result will be j omega V0 plus e power minus j beta z, where V0 plus e power minus j beta z is the original phasor. Let me denote all my phasors by drawing this small arc on the values, and this phasor will be dependent on z because of the factor e power minus j beta z. Therefore, I write this as V0 plus of z. Okay. And there is a term which is getting multiplied to this V0 plus of z phasor, and that term is j omega. So, if I represent this one in terms of its phasor, this would be V0 plus e power minus j beta z, and when I differentiate this one with respect to time, this is as though I have simply multiplied the phasor by j omega. So, differentiating this del t of the original cosine waveform is equivalent of multiplying the phasor by j omega. So, mathematically del t in the phasor domain becomes multiplication by a factor j omega in the phasor domain, as I said. Okay. Similarly, you can show, I will not show it here, I will leave it as an exercise. The act of taking an integration with respect to time will be equivalent in the phasor domain of dividing the phasor by the factor j omega. Okay. These simple rules will actually help us in writing the equations in a slightly better and a mathematically simpler form for us. Okay. So, this is the phasor notation which I wanted to introduce you to. There is nothing specific about a voltage phasor. I can as well consider the current phasor. I will have I0 plus of z, or I will have I0 minus of z, both being the current phasors. Now, let us get back to an interesting thing. We know how to obtain the voltage as a function of z and t on the transmission line. We also know how to obtain the corresponding phasors V plus of z or V minus of z, or V0 plus of z and V0 minus of z. Can I actually obtain what is I of zt from the voltage? It should be possible for us to do so, right? I should be able to obtain what is the current from the voltage. In order to do that, I simply need to go back to the original equation for the voltage. Remember, when we were applying the Kirchhoff's voltage law, in order to relate voltage and current, we said that the total voltage change del V by del Z is equal to minus L del I by del T. Now, instead of considering this voltage V and I, if I go to the phasor domain, then del V0 plus of Z would be the phasor representing the voltage here. That change with respect to Z will be given by del V0 plus of Z by del Z. This is the partial derivative of the phasor with respect to Z. This would be equal to minus L into j omega, and the current phasor, let us call this as I0 plus of Z. Okay. Oh, I need to denote my phasors by this bar that I am putting. Please note that I have gone from the Z and T kind of a notation to the phasor domain. Okay. So, I have gone to the phasor domain by changing these voltages and currents into their appropriate phasor. Okay. However, I do know that V plus of Z phasor is given by the amplitude V0 times the factor e power minus j beta z. If I take the derivative of this one, what would I get after I take the derivative? Now, I do not even need to have the partial derivative. These partial derivatives can become total derivatives because the dependence on t has been taken away, right. So, if I differentiate this voltage phasor with respect to z, what do I get? I get minus j into beta, right, and then whatever the original V0 plus e power minus j beta z, that would still remain. So, now equate this one with this expression for the right hand side and take out all the minus sign out there. J will also cancel on both sides. So, what you get is omega L I0 plus of Z phasor is given by V0 plus of Z phasor into beta. Okay. I know that the ratio of voltage to the current must be some kind of a impedance. Okay. This impedance in this particular case is defined as the ratio of positive going voltage to the positive going current. That is, both voltage as well as current are going along the plus Z direction. That is, both of them are traveling along the plus Z direction, and this ratio will be denoted by the quantity Z0, and this Z0 is called as the characteristic impedance of the transmission line. Okay. And this characteristic impedance can be of course complex, but in most practical cases this characteristic impedance will be a real quantity. And what is the characteristic impedance? Use this equation to bring I0 down here and beta onto this side. This is given by omega L by beta, right. But what is omega L by beta? I can simplify this further because I know the relationship between omega and beta, right. So, I have omega by beta into L, but omega by beta is nothing but the phase velocity up into L, up, the phase velocity, is simply given by 1 by square root of LC for this particular lossless transmission line. Multiplying this one by L will give you square root of L by C. So, the characteristic impedance of this transmission line is purely real, assuming that both L and C are real and L and C are both positive. In some cases it may not be so, but in our case we assume L and C to be real quantities and positive quantities, and therefore Z naught will be a purely real quantity. Okay. This purely real number or purely real quantity is also very interesting. It is completely independent of the frequency. Okay. It is completely independent of the frequency. The only quantities on which it depends are the characteristic values of the inductance and the capacitance of the transmission line itself. That is the reason why it is called as characteristic impedance. It is the impedance, or it is the characteristic of a given transmission line. It has nothing to do with the frequency. Of course, these are approximate results, because in practice there would be frequency dependence, because we have considered only lossless transmission line. It turns out that for a lossless transmission line the characteristic impedance will be purely a real quantity, and since it is purely real quantity, sometimes instead of denoting it by Z0 we denote it by R0. Okay. The definition of characteristic impedance can also be obtained by considering the negative going voltage and the negative going current. This is V0 minus to indicate that this is a negative going voltage, okay, and this bar here or this tilde indicates that this is the phasor that I am considering, and the characteristic impedance is actually defined as a minus sign over here. So, because this minus sign appears because current will be going in the other direction. Okay. So, because of this reason the characteristic impedance will be defined by writing this as minus V0 minus of Z by I0 minus of Z. Okay. So, this characteristic impedance value will also be equal to square root of LC. This is appropriate when you have a negative going voltage and a negative going current. Okay. So, to summarize what we have been looking at so far, we started off with the equation del square V by del Z square equal to LC del square V by del T square for the voltage, and then we showed that voltage V of ZT, that is changing along the transmission line, is actually a wave which is propagating along either plus Z direction or minus Z direction. Mathematically there is no reason why you cannot have both plus and a minus direction, but in case physically there will be one direction that is preferred, or both, depending on the situation that we consider later on. Okay. The solution of this can also be written in terms of the phasor, and all solutions of the form g of z minus or plus t by square root LC are admitted as a solution of this wave equation. Finally, we define two quantities. One is called as the characteristic impedance, which is Z0 given by square root of LC. We also define the phase velocity as omega by beta. Okay. So, we will say more about all these quantities in the next module, where we will consider terminating a transmission line. Thank you very much.